All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another exciting episode of Math 212, Calculus 2, and
1XW.
1XW, like 1XW, yeah.
Summer 2020 semester.
Yeah, that's right here. We're out here hustling, like and subscribe. Okay, whatever. All right. Like 1XW gang with the gang leader, Kayla. Yeah. Yes, we have a very retro, as someone put in the comments, topic to talk about today. We're going to revisit lines. Equation of lines. So yeah, that thing you did in high school. Then you went to college and you did college algebra and they told you, oh, here's the equation of a line. And then you went to pre-calc and they're like, here's the equation of a line. And then you go to calculus and they're like, oh, you remember the equation of a line? We're going to generalize the slope of that guy, right? It's like equations of a line. Like, oh my God, equations of a line. We're going to do it again in Calc 2, unfortunately, or maybe fortunately. Okay, Jason, you're really dying over there. Jason's like really dying. Yeah. All right. What do you know about the equation of a line? Everybody, what's the equation of a line? Let's start there.
Y equals mx plus b.
Y equals mx plus b. We all agree, right? Everybody knows that. Yeah, we're typing in the comments y equals mx plus b. Awesome. No, that is incorrect. Y equals mx plus b is not the equation of a line. And no, I see you trying to be fancy with your y minus y1 equals m times x minus x1. Not the equation of a line. Yeah, nope. Nope. So today, I'm going to give you the red pill. I am going to tell you that no.
Is it rise over run?
No, that would be the slope of a line. Back in the day, you used to hear about the slope of a line, but no, that's not even the slope of a line anymore. And y equals mx plus b is not the equation of a line. Let's actually talk about it. Right, so not as retro as you would think. Okay, so let me show you the truth. Boom. All right, so y equals mx plus b is the equation of a line. False. That is a plane. Remember that we did this in a previous lecture where I asked you to sketch things like x equals 1, sketch y equals 1, sketch z equals 3 or whatever. Remember? That was when we sketched those. What were they? They were planes. They weren't lines, right? So when you saw y equals 1, now before this class, you thought of that as a line. In algebra, it was a line. In high school, it was a line. In Calc 1, it was a line. Y equals 1. Oh yeah, that's just a horizontal line. Actually, the real truth is y equals 1 is a plane. So anything that looks like y equals mx plus b, it's actually a plane. So yeah, it's not a line. So all these years they've been lying to you. You know, it's kind of like when you were young and they told you that you can't subtract a bigger number from a smaller number, and then you go and learn about negative numbers and you're like, what? Why did they told me that this couldn't happen? Yeah, but nope. Once upon a time they told us that x squared plus 1 equals 0 had no solution. Then you found out about complex numbers and it's like, what is it? What are they not telling me? So yeah, we are slowly revealing the truth behind the universe. Okay, so we're going to cover equations of lines, and we're going to do equation of planes while we're at it, since most people's conception of a line is actually a plane. We're going to actually cover both of those. All right, so let's actually jump into it. Let's start with lines. So if y equals mx plus b is not the equation of a line, what is the equation of a line? Let's actually figure it out. So, let's actually figure it out. So let's say here we're in 3 space. And let's say I have a line. So the red thing is a line. Okay, so that's a line. Now what we want is what the equation of a curve is just an equation that allows you to find any arbitrary point. So back when you learned erroneously that y equals mx plus b was the equation of a line, why was that the equation of a line? Well, it tells you the x comma y coordinates on something that looks like a straight line. If I plug in an x, I can find the corresponding y. In the same way, if I take a random point on this thing, x comma y comma z, I want to be able to find an equation that describes this point. Right? So that's what we actually want. And how are we going to figure it out? Well, remember back in the day when you were trying to find the equation of a line, you needed two pieces of information. You need a point on the line. You need some sort of reference point, some kind of way to get fixed to the line. Then you needed a slope, which tells you what direction you're moving as you pass through that point. We're going to be doing the same thing here. So what I'm going to do is we're going to start with some other point. So start with a point here. So call this x naught, y naught, z naught.
You know what I'm assuming actually, Professor?
Or let's actually call it ABC. So let's say a point here, ABC, is a point on the line. And so this is just some arbitrary point. Oh no, I did call it x naught, y naught, z naught in the thing. So let me stick with the notation. X naught, y naught, z naught. So this is some arbitrary point on the line.
You know what I actually assumed?
Just let me finish, Jason. So now here's what we're going to do. So I have a point on the line and I need a direction. So what we're going to do is, suppose I can find the direction of a line. So here's a vector v. This is a vector in the direction of the line. This is going to function in the same way that the slope functioned for us way back in the day, vector in the direction of the line. In other words, the vector that's connecting the point I know to an arbitrary point, that vector must be parallel to the vector v. In fact, it's a scalar v. Let's call it t times the vector v. And here's what I'm going to do for the point. I'm going to take a position vector that goes from the origin and hits that point. I am going to call that vector r naught, right? That travels to x naught, y naught, z naught, okay? So this is the vector x naught, y naught, z naught with angled brackets. Then let's say I'm going to take some other vector that is going to travel towards this point over here that hits that arbitrary point. Let's call that vector just r. So I have this line. I know a direction it's moving in. I know a point on the line. Then what I do is I use two vectors to hit 2 points on the line. One of them hits the point that I know about. One of them hits an arbitrary point. Now, what you're going to notice is that we've just created a certain scenario. So basically what we have over here is I have boom, r naught. I have another vector going boom like this way, t times v. And then I have another vector, boom, calls r. And r is the guy that I really care about. That is the vector that gives me the arbitrary position, x comma y comma z. By vector addition, you actually know how these guys relate to each other. If you take the white vector, it appears white here, but when I print it out, it's going to be black. So I don't want to write down the white vector. The white vector plus the blue vector will actually add up to give you the green vector, right? So what you'll notice by vector addition, you will get that the vector r is given by the vector r naught plus the vector t v, where t is a parameter. And that's it, ladies and gentlemen. That is the equation of a line. Not y equals mx plus b. A line is a fixed vector plus a parameter times some other vector that's in the direction of the line. The equation of a line is this guy. This leads us to, this is the equation of a line. Now, of course, we can actually flesh these guys out, okay? Because I can do something like, yes, once we're in 3 space, vectors is how we get around. We can use vectors to figure out a lot of things. We're also going to use vectors to figure out the equation of a planes, but we're getting ahead of ourselves. Our r was just the position, the position vector for the arbitrary point that. Our r naught was the vector which is had position for the fixed point, this guy. And if I set v to be a comma b comma c, then if I plug into the above equation, I would get x comma y comma z equals x naught, y naught, z naught plus t times a, b, c. Then I could multiply the t into the second vector. And then combine the vectors with another vector addition. And that gives us this equation down here. So that is the equation of a line. You can think of the equation of a line as a vector. What we're looking at right now is called the vector equation of a line. This guy is the shorthand. And this guy is kind of fleshed out when you want to see where would I plug in each coordinates. So basically, if we know that a line passes through the point x naught, y naught, z naught, and its direction vector, a vector that's parallel to the direction of the line, is a comma b comma c, then the equation of the line is given by the vector x comma y comma z equals x naught plus at comma y naught plus bt plus z naught plus ct. This is the equation of a line. This is the vector equation of a line. It turns out that there are many forms of the equation of a line in 3 space. So here's another way we can talk about the equation of a line. Notice here that I can just, by vector equality, if 2 vectors are equal, the corresponding components must be equal. So I should be able to say x is equal to x naught plus at, and y is equal to y naught plus bt, and z is equal to z naught plus ct. This is, as you will notice, this is like a set of parametric equations. They describe each coordinate as a dependent variable of some other variable, which we call a parameter, which is the t. So this is the parametric version of the equation of a line. And this was the guy that Jason typed into the chat box earlier. So now we can see how he got it. So that leads to this. Now these two are very important. These 2 versions of the equation of a line, the vector form and the parametric form, you need to know both of these forms. You need to know them very well. You need to know how to plug into them. You need to know when you read them, what you're looking at. You're actually looking at the equation of a line, etc. There's a third form, though. It's not very common, but there are sources that will use this form. And if you see this in one of those sources, you should know what it is. And this is the symmetric form. Basically, if I solve for t in the above, in the first one, I would get t is equal to x minus x naught over a, as long as my a is not 0. But I would also get that if I solve for the second equation in the y equation, I would also get my t is y minus y naught over b. And I would also get t is z minus z naught over c. And this is another type of equation. If you see this kind of double equation, x minus a number over some other number equals y minus a number over some other number equals z minus a number over some other number, that is also the equation of a line. That leads to what we call the symmetric version of the equation of a line. Not very common, not commonly used, but you should know it, really. The vector form and the parametric form are much more common when someone wants to describe a line. So from now on, this is what you know a line is. It's not y equals mx plus b. It's x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. The nice thing about a line, one way you can look at a line is in the shorthand form. It's a fixed vector plus a parameter times some other vector. That is what a line is. And the nice thing about that form is that no matter now what dimension you go into, a line is going to look like that. So you see how all your life they were telling you a line was one thing, and now we got to Calc 2, we have to tell you that a line is another thing. It turns out now you know the actual truth. Even when you go to higher dimensions, a line is going to look like that thing in the box. You might have to add extra components to go into higher dimensions, but other than that, the form is the same, and the structure of computing it is going to be the same. So from now on, this is the equation of a line, now and forever. You will also notice that if I were to take this equation of a line, go back to 2 dimensions and do the elimination of the parameter strategy that I told you guys when we're doing parametric equations, you would develop the y equals mx plus b back in 2 space. So that actually, it does include that definition, but the y equals mx plus b was a very limited definition. It didn't tell you the full story. It was only a story that was true in 2 space. Y equals mx plus b is a line in 2 space, but that was because it was the shadow of a plane that was slicing through 2 space. There was way more going on than you realized. But now we know the truth. This is the equation of a line. Now, you might be wondering, what if one of the components of the direction vector is 0? Won't this version of the equation of a line have trouble? Well, when that happens, usually we just remove that part from the equation, and we just write x equals the constant separately. So for example, here, so if the a was 0, I would just write x equals x naught, put a semicolon, and put the other 2 in that form. Or if the b was 0, I would put y equals y naught, and then put the other 2 in this form, and so on and so forth. So this notation is a little bit cumbersome because if you have a certain scenario, you would have to change how it looks. So people like using the vector form and the parametric form. These are the guys that you should know. So if you're reading anything and you see equations like this from now and to any point in the future, you can know it's going to be a line. And that's never going to change anymore. So now you know the truth, and it'll always be like that. You're not going to go into some other class now. They're going to be like, remember in Calc 3 when they told you this was the equation of a line? No, not true. No, you now know the truth. You have taken the red pill. We now know the truth. This is the equation of a line. All right, let's actually do some examples. Let's work around with this definition. And afterwards, we'll do these examples, but let's move this out of the way. These aren't the guys we're ready for yet. So let's do some examples. These guys are very... All right, so let's get some practice using this new equation of a line, because when you first learned y equals mx plus b, you had to practice a lot of problems to get used to it. This is not going to be any different. Find the vector and parametric forms for the equation of a line that passes through the point 1, 2, 3, and it's parallel to the vector -1, 0, 2. So we have a line. I know it passing, so here we have a line. Boom. I know it passes through a point 1, 2, 3. And I know a vector that's parallel to the line is the vector -1, 0, 2. How do I find the equation of such a line? Well, I would realize that my 1, 2, 3 is going to be the x0, y0, z0. I would also recognize my -1, 0, 2. That is going to be my a, b, c. And so this just means the equation of the line is x, y, z equals x0, y0, z0 plus t times this other guy. And that's it. That's the vector equation. That's it. I have the point and a direction. It's kind of like how when you in two space, when you had the point, you had the slope and the y-intercept, you could just immediately plug it into the equation of the line that you had back then. Same thing here. I have a point and a direction. That's all I need. I can just plug this in. This is the vector form. Or I could actually combine both of these and say x, y, z equals 1 minus t, comma, 2, comma, 3 plus 2t. What you'll notice about the equation of a line in vector form is that the components individually will look like y equals mx plus b. You'll have a number times a variable plus a constant, right? Where your variable here, though, is the parameter. It's not the x variable. It's some other variable that we're measuring the x in terms of. So if the components look linear from what you remember linear meant in all your math classes before this, so you have a vector function where each component looks like mx plus b, that is the equation of a line. Now, in order to get the parametric equation, I would simply just match these guys up. So to get the parametric equation, equate the components. So this means that your x is equal to 1 minus t.
Y equals 2 and z equals 3 plus 2t.
Right. That's the parametric equation. Now, normally we put limits on our parameter. Here, of course, if it's a whole line, it's going to run sideways from -infinity to infinity, right? And that will trace out the whole line. So that's the equation of this line. So this is the parametric form. And that's the equation of the line. So a line that passes through 1, 2, 3, and it's parallel to the direction -1, 0, 2, this will be its equation. This will be the vector form of its equation. This will be the parametric form of its equation. Any questions so far? Okay, so far so good. All right, so that's it. That's the equation of a line. Let's do some other examples. Let's do this one. All right, find the equation of a line that passes through this point and that point. Then tell me, where does this line intersect the YZ plane, XZ plane? And then where does the line intersect that surface? Let me break these guys up. All right, what are we doing here? You guys tell me how to find this line. I gave you 2 points on the line. How do I find the equation of the line? Ideas. So I have a line here. boom. I know it goes through the point -1, 2, 0. It also goes through the point 3, 1, 2. How are you getting that? So you think it's -1, 2, 0 plus t times 3, 1, 2? Oh, switch them? Yes, we need the parallel vector, right? So you know what we need. How do we get that vector? No, because a dot product is a scalar. Dot products do not give you vectors. Okay, cross product of what? Right, you guys are thinking way too complicated. It's not a dot product or a cross product or any of that. Simply just find the vector that connects the 2 points.
What I'm assuming probably would be 3 minus -1 equals
Right.
4. 1 subtract 2
Right,
is
subtract final
-1.
minus initial. If I
And
want
2
this
minus
vector,
0 is 2. And what you would actually get for the vector would get 4, -1, 2. And the original coordinates would be -1, 2, 0. So what I'm assuming would be x equals -1 plus 4t, y equals 2 minus 1t, and z equals 2t.
right.
So
So
therefore,
you just want a vector that's parallel to the line. So just connect the 2 points on the line. A vector that connects the 2 points on the line will necessarily be parallel to the line. So I can use that as my direction. As for the point, I can pick either one. Let's pick the first one just because that's going to be my x naught, y naught, z naught.
so in this
And yes,
point,
I could pick the other point. It does not matter.
so I would say -1 plus 4t, comma, 2 minus 1t, comma, 2t in vector brackets, like, which is in vector form.
So this would be -1, 2, 0 plus t times 4 minus 1, 2, which you could write as -1 plus 4t, 2 minus t, and 2t.
That's what I said.
Right? There we go. That's the equation drawing line.
So if the x0 switch, by the way, you would still get the correct answer if the x0
Yes.
switch?
Yes. You'll trace out all the same points. You might need a different t value to hit a certain point, but ultimately all the points that you hit will be exactly the same. So even if I put the 3, 1, 2 here, we'll get the same thing. You'll notice here, like if I put t equals 0, this will give us the point -1, 2, 0. What you can notice is if I put in t equals 1, this will give me the point 3, 1, 2. So I would get back the point 3, 1, 2 anyway. Yeah. All right, follow-up question. Where does this line intersect the XZ plane? Ideas.
Are you asking for a point or a vector?
Where is a location?
Oh,
So it's a point. A vector would be a direction. So if I ask you what direction is this moving in, then you would answer with a vector.
okay.
Right. So for the XZ plane, remember this means y equals 0. The y coordinate is 0 along the entire xz plane. So this means set y equals 0. But that would mean 2 minus t equals 0. And that would mean t equals 2. And so go to the line and plug in t equals 2.
Right, that means in brackets, in those vector brackets, it means 7, 0, 4.
So you would have x is equal to minus 1 plus 4 times 2. Your y would be 0, and your z would be 2 times 2. So you would get the coordinate 7, 0, 4. That is the location. So this line, it will pass through the xz plane in this particular coordinate. It will pass through when the x is 7 and the z is 4, but your y would be 0.
Why not? Why can't you just put in vector brackets rather than
Because a vector and a coordinate are different. A vector is direction. I am looking for a location, not a direction. If I put a vector, so this is like a point. If you put 7, 0, 4, that's a vector. These are two different objects. Right? We're looking for a location here. We were asked where. Okay. Third follow-up question. Where does the line intersect this surface? X plus 2y minus 3z equals 5. Now, don't worry about what that surface is. I'll tell you, it's actually a plane, but we're going to figure that out later on. We're going to be able to recognize that that would be a plane. But there's a plane, and this line is going through space, but it eventually cuts through this plane at some point. It pokes through this plane. What point would that occur at? And again, it's where, so we're finding a point here. Ideas. How would I set them equal to each other? One is a scalar equation, one is a vector equation. Right. So the idea that you were thinking, but you probably didn't say it clearly, is you plug them in. We know what x, y, and z are. X is this, y is this, z is that. So we're just going to plug those guys in. So this means I have minus 1 plus 4t plus 2 times 2 minus t plus or minus 3 times 2t equals 5. Now all I'm going to do is solve for the t value that will make that true. And then I can actually just find the coordinate from that. So here I would have minus 1 plus 4t plus 4 minus 2t minus 6t equals 5. Minus 1 plus 4, so that's 3. Here I'd have minus 8t plus 4t, this is minus 4t. And so now if I move that over, I would get minus 4t equals 2. So t equals minus a half. Then now I go back and plug that in. This means my x should be 1 plus 4t. When I plug in t equals minus a half. That's going to give me minus 1 minus 2, that's minus 3. My y is going to be 2 minus t. When I plug in t equals minus a half. that is going to be 2 plus a half, which is 5 over 2. And then my z is 2t. I'm going to plug in t equals minus a half. So that's minus 1. And so it intersects at minus 3, comma 5 over 2, comma minus 1. And that's our location. Location, location, location. All right.
I have a quick question.
Yes.
So if we were to be given a problem like this on an exam,
Mhm.
so the keywords to look at or should be, if you have a question where it says where, that's when we should find a point. But if it says in what direction, is that when we should be looking for a vector?
Yes. Vectors give direction. Points give
Okay.
location. Yes.
Okay, got it. Thank you.
All right. Now there's actually nothing new for me to teach you here. What I taught you about this topic in parametric equations still holds true right now. So you won't have to learn anything new. Yay. Line segment from this point to that point. Tell me how to do it. You could actually do this using the formula that I gave you, but I gave you a shorter formula way back when we're doing parametric equations. How do we find the x component of a line segment? That's right, proverbial student. You start with where x began, then you find what you need to add or subtract to get to the second point, and then you attach a t. For the y, you start where the y began, find what you need to add or subtract to get to the second point, add a t. For the z, you start where the z began, find what you need to add or subtract for the second point, add a t. Then set
It
your
should be
t to go
3.
between 0 and 1. So that leads you to the parametric equations. X equals 1 minus 4t, y equals 2 minus 2t, and z equals 3 for t between 0 and 1. That will give you the line segment. One thing I want you to notice is that this will coincide. Notice this coincides with our formulas above. So you're in a test, hell freezes over and you forgot the method that I just told you. And so you're not going to get the answer in a few seconds. It probably now is going to take you a couple minutes because you forgot the shortcut that I told you before. You can still figure it out. All you need to do is find a vector that goes from this point to that point by subtracting them. That you are going to notice is going to give you the coefficients of t. Then you just pick a random point and then put it that in the formula r naught plus t times v. So your v would be the vector that goes from here to here. And you'll notice that it is final minus initial, which coincides with the form that I gave you before, where it was x1 plus, in open parentheses, x2 minus x1 times t. That x2 minus x1 was like the final point coordinate minus the initial coordinate. So going back through the formulas and doing that, you could figure it out. But you should actually know how to create a line segment very quickly. And you should be able to do it the way I just did it here. And you won't need to go through some formula.
Professor, why isn't it like, in bracket forms, -1 plus 4t, comma 2 minus 1t, comma 2t, or like, whatever you got, like, or should I say, why isn't it bracket, -1 minus 4t, comma 2 minus 2t, comma 3?
Because this is the parametric form.
Parametric form?
What you're describing is the vector form.
So is it the same, by the way, just written in different
Yes,
forms?
it is the same.
So if this was a multiple choice question, and if you were to figure out which answer choice would be
Yeah, so
when
let's
the
say
vector,
you wrote the answer like this, and in the multiple choice, you saw this, then you would make that choice because they're exactly the same.
I mean, like you said, multiple choice, right?
Yeah.
If it was multiple choice, what are you trying to say? Like, I've written this, suppose this is my answer.
And the multiple choice could
and
also, instead of 1, 2, 3, it could have a different position. It could also have -3, 0, 3. And it would also be a choice that you pick. They're the same. This is another one of the a half versus 0.5. If someone writes it on a half, someone writes on 0.5, they wrote the same thing. It just because it looks different doesn't mean they're not the same thing. I use this equation to figure out that equation, and I use this equation to figure out that equation. They're all the same. They're all the same. There's no difference between one versus the other. The problem, the question did not ask me for a specific form. It just says give an equation for the line. It never told me specifically give a vector equation for the line, which means I can give an equation in any form I want. This is one of the forms, parametric form. I did it just because, arbitrarily, on a whim, and it won't matter because it's the same. See, it's one of the forms of the equation of a line. It's this form right here. All right, let's talk about, that was the last example. Let's talk about some important things. We want to talk about how lines can relate to each other. Now, it turns out that when you were in two space, the way that lines could relate to each other were actually very, there weren't a lot of different ways, actually. Let me move these guys over here. So in two space, you might have remembered that you can either have lines that are parallel and they never touch, but the moment that two lines are not parallel, they will have to touch at some point, right? In two space, it was an inevitability, right? If two lines aren't parallel, they have to intersect at some point, right? Now, if they're parallel, it's possible that they will never touch each other. They will have no points in common, or they actually coincide and all their points are in common, okay? So you can have lines that are not parallel and lines that are parallel. Lines that are not parallel have to intersect. Lines that are parallel may or may not intersect, but if they do intersect, they will actually intersect for all points. In three space, this is no longer true. It turns out that you can have lines that are not parallel and at the same time that they will not intersect each other. This is called skew. So two lines in three space, they can intersect, they can be parallel, or they can be skew. There's a third option, right? So in two space, this is not true, but in three space and higher, this is true. You can just have one line. You can have two lines that are not parallel, but one is just in a different plane of existence than the other. And so they'll never actually touch, and at the same time, they're not parallel. And so what you need to be able to do is you need to be able to distinguish when two lines share these various types of relationships. And we therefore need to know how to identify these types of relationships. So that's what the box here is about. So that you can know these kinds of relationships. Two lines are parallel if their direction vectors are parallel. If your direction vectors are pointing in the same direction, you're parallel. Right? Now, you may or may not intersect when doing this, but if you do intersect, you'll actually intersect for all points. That's still true. Two lines are orthogonal if their direction vectors are orthogonal. So if I have one line and I want to know, is this line perpendicular, aka orthogonal to some other line, all I need to do is isolate the direction vectors, and then if the direction vectors are orthogonal, then the lines are orthogonal. Now, the third bullet point is the important thing. This makes three space and any space higher than three space distinctly different from two space. There are three options for lines now. A line can be intersecting, You can be intersecting in parallel or intersecting in non-parallel. If you're intersecting in parallel, then you intersect at all points. It is also possible to be skew. Skew means you are neither intersecting nor are you parallel. So you never touch and you're not going in the same direction, okay? You guys are destined to just be apart forever, okay? So let's actually determine that. Determine whether these lines, I gave you a pair of lines, L1 and L2, and there are 3 examples here, but let's go through one at a time. Determine whether the given lines are parallel, intersecting, or skew. If they intersect, find the point of intersection. Okay, so these are 2 separate lines. I'm measuring them by 2 separate parameters so we don't get the parameters mixed up. The parameter here is S, the parameter here is T. So my first line is this. Notice it's in parametric form. My second line also in parametric form. And this is line 1 and line 2. So the question is, do these lines intersect? Or are they parallel? Or are they skew? And Jason is already saying they're probably skew because he just doesn't believe anything's going to work out. They don't have to be skew. Let's actually see. How would we actually know? Here's a nice way to know. Since we want to use their direction vectors, right? Based on the bullet points that I gave you above, the direction vectors is going to be have a lot to do with our conclusion. Find the vector forms is probably how I would start. So notice my L1, I can think of this as the coordinate it passes through is what? Tell me a coordinate that this line passes through. The easiest one. L1, what coordinate does that pass through? Give me a point on that line. Make it a little bigger. I don't know if you guys can see. Right, 6 minus 2, 5. So that's here, 6 minus 2, 5. Plus t times, what's the direction vector? Minus 3, 2, 4. Now I do the same for L2. Ten, 3, 7, plus a parameter times minus 6, 4, 8. All right. Now give me the conclusion. Are these lines parallel? Do they intersect or are they skew? Let's start with parallel. Are they parallel?
Only the T and the S, the vector parts, but not really like, the origin, the original parts, which are the points I meant.
Okay. So remember what the bullet point says. 2 lines are parallel if their direction vectors are parallel, which means the points irrelevant. You shouldn't even be looking at that.
So I guess they're parallel.
How do you know they're parallel?
Because if you divide them by 2, you would figure out it's parallel.
Right. If I divide the second one by 2, I get the first one, meaning one vector is a scalar multiple of the other. How do I know the lines are parallel? Since if I take 2 times this one, I would get the second one, which means one vector is a constant times another, which means they're parallel. So in this first example, these 2 lines are actually parallel. They're going in the same direction. All right, let's look at another example. What about these 2 lines? So we'd first do the vector forms so we can see nicer. X, Y, Z equals, then I have equals equals. It's not programming. X, Y, Z equals 2, 3, 1 plus T times 4, 0, minus 1. Then my L2 Okay, are they parallel? Do they intersect, or are they skew?
I'm assuming they're intersecting is because if you were to think, if they're not parallel, and if you were to think about intersecting, I mean, like, honestly, don't ignore the original points.
Right.
However, if you were to think about, like,
So you look at these,
look at these, they're not
and you
parallel.
realize not parallel.
But however, you can figure out they're intersecting because if you were to plug in, like, you see there
Right
is
here,
no
they're the
vector
same.
for, like,
So
for
here,
line 1.
pass through same point. So they are intersecting. Now, it's not always obvious that they pass through the same point. So let me actually show you, if you didn't see the point right there, just staring you in the face, that they're definitely intersecting, that they pass through the same point. Let's say it wasn't this obvious. How would you go about doing it? What you would do is you would set the components equal to each other. And see if you can find values of the parameters that make the equation true. So, for example, what I would do here is I would set the x coordinates equal to each other. So this means 4t plus 2 should be equal to 2s plus 2. Then I would set 3 equals 2s plus 3. Then I would set s plus 1 equals minus t plus 1. And now I try to see, does this system of equations have a solution? Now you'll notice that there are 3 equations and 2 unknowns. So what you do is solve for the solution from 2 of them first, and then solve for the third. So for example, so what we do now, solve 2 equations simultaneously. Then check if that answer works in the third. So what I'm going to do, let's pick these 2 to solve because they look simpler to work with. So what I'm going to do here is let's solve 1 and 2 first. So what I realize from 1, we get s equals 0 right away. Now I plug into 2. And I would get minus t plus 1 is equal to 1, which means that my t equals 0 as well. Then I would try in the third. So equation 3 is going to become the following. I'm going to plug in 0 for t. Then I'm going to plug in 0 for s. This means that 2 equals 2, which means, yay, that works. So this means they intersect. Now, of course, in this case, it was very obvious because the points were just staring us in the face, but it's not always obvious. So if it's not obvious, this is how you would have gone about doing it. You literally set the coordinates equal to each other, and then you check, can I find values of s and t that will literally make the x coordinates coincide and the y coordinates coincide and the z coordinates coincide all at the same time? Because if that happens, that means they're at the same point. So this one was obvious that they intersected just by seeing that they both pass through 2, 3, 1. But in the non-obvious case, this would be the process that you would go through. If it doesn't work when you plug it into the third equation, it means it does not intersect. Because you would have found where 2 coordinates coincide, but not the third. And that's not good enough for intersection. If the system has no solution, including if you found an answer for 2, but it doesn't work in the third, the lines do not intersect. Right, because to intersect, it means your x, y, and z coordinate have to all be the same at the same time. So if you get 2 coordinates to work together, but you don't get the third to work together, then you're not going to intersect. Okay, so I gave you an example where they were parallel and an example where they intersected. So I guess you can probably guess that this is an example that's going to be skew. So you can see what is going to happen here. I think I picked an example of the third variety. So let's actually see what would happen here. So here are my 2 lines. The goal is to figure out, are these guys parallel? Do they intersect? And are they skew? Or, right? You can't be intersect and skew at the same time. Okay, so again, I would go with the vector equation. This time I know they're skew. Yeah, you said that the first time, Jason. We couldn't trust you. So you said the first example was skew. How do you know?
Because of the original points. That was the reason, the original points. Yeah. And you have to solve for the original points.
Okay, so this is going to be 0 to minus 1 plus t times 3 minus 1, 1. L2, x, y, z. And you should be practicing reading off the coordinates like I'm doing here. So you shouldn't be taking too much time doing this part. So now you look at this and you realize, oh, not parallel. How can you tell that these are not parallel? It means one is not a multiple of the other. How can you tell one is not a multiple of the other? Well, all you have to do is pick your favorite coordinate, say the second coordinate, because they both have like 1s in them. Figure out what number you have to multiply one coordinate by to get the other one, and then realize that if I multiply the other coordinates by that same number, I would not get the others. For example, to turn the second coordinate of the 1 into the other, I would have to multiply by -1. However, if I multiply 3 by -1, I don't get 4. If I multiply 1 by -1, I don't get -3. So a constant of proportionality between one component does not work for all components, and therefore I know it's not parallel. Now, it's not obvious if they intersect or not. Because yes, I can see right now they don't pass through the same point, but maybe there exists values of t and s that when I plug those in and add these two vectors that they become the same point. So it's not obvious if they intersect. So what we're going to do is I'm going to actually set up that system of equations. So that leads me to doing the following. My 3t equals 1 plus 4s. My 2 minus t is equal to s minus 2. And my t minus 1 is equal to -3 minus 3s. So I have this system of equations here. Now I'm going to want to be able to solve this system. So let's say none of these look particularly nice. So let's just call this 1, call that 2, call this 3. And I'm going to focus on these first. So then in 1, notice here that I have 3t minus 4s equals 1. So that's my equation 1. In the second one, I would have, if I bring it to one side, minus t minus s equals, if I bring the 2 to the other side, I get minus 4. So this is equation 2. What I can do here is I can multiply equation 2 by, say, 3. So this is 3t minus 4s equals 1. And then minus 3t minus 3s equals minus 12. So this is equation 1. This is equation 2 times 3. And now what you realize is I can add these guys. Here I would get minus 7 equals minus 7s equals minus 11. In other words, my s has to be 11 over 7. In 1, or let's do in 2, this would mean minus t minus 11 over 7 equals minus 4. This means your t would be 4 minus 11 over 7. It's 28 over 7 minus 11 over 7. That's going to be what? 17 over 7? So that's your t value. Now what we do is we try in the third. So my third equation looked like this guy here. T minus 1 equals minus 3 minus 3s. And I'm going to plug in here, I'm going to plug in 17 over 7. And in here, I'm going to plug in 11 over 7. Now on this side, I would have 17 over 7 minus 1. This is going to be 10 over 7. And on this side, I would have minus 3 times 11 over 7. This is going to be, well, that's going to be negative. So here, I realize not equal. So it does not work in the third, and this means they are skewed. So they're not parallel, and they don't intersect.
That's what I said.
And that is our example.
That's what I
don't have
said.
any,
I
I
told you
don't
that
have any
there's skew.
more examples here.
I told you that there's skew.
So I think that's all we have for lines. Let's move on to planes. Yay! Okay. Boom. All right, let's talk about planes, right? How do you find the equation of a plane? We're going to construct one again. So last time we spoke about an idea called a normal vector, which means if I have a plane and I wanted to talk about the direction in which that plane is moving, the best direction to describe the direction of a plane is a direction normal to the plane. We explained why this was. I did that whole thing with the textbook and the pencils and looked like an idiot doing it. So I'm not going to go over that again. So here's the thing. I have a plane. There's an arbitrary point in the plane, x comma y comma z. We want an equation that describes this arbitrary point. Like, do it again. Whatever. Kayla's messing with me. We want an equation that describes the arbitrary point. Tell me an equation that would describe x comma y comma z for this random plane, and that's the equation of the plane. Now, just like with a line, we need a point and a direction. So here's a random point. Let's suppose I know a point in the plane, x naught, y naught, z naught. And let's say I know a normal vector to that plane. So let's say I know a vector like this, pointing up. It's perpendicular to the plane, and call that n. This is my normal vector. Let's call that ABC. So I know a direction. Now what we can do is we can create a vector that goes from that point to the arbitrary point. So I can call this vector, it will be x minus x naught, comma y minus y naught, comma z minus z naught. All right, so what is the relationship between these two vectors that I just drew? They're orthogonal. How can I describe orthogonality between two vectors? What does it mean for two vectors to be orthogonal? Two vectors are orthogonal. What's the first thing that comes to mind, or should come to mind, if you're a Cal 3 student? Well, yeah, but that's too Captain Obvious. Yes, orthogonal literally means perpendicular. Orthogonal does not mean they equal 0. No. Orthogonal does not mean intersect. No. Abdullah has it. So, yesterday, there was a little box, a little maxim around here somewhere. I don't remember exactly where, but yes, this one, the thing that's triple asterisked. Remember that guy yesterday? And remember I said from now on, whenever you hear the words perpendicular or parallel or orthogonal, think of this box. Remember that? Yes. Orthogonal if the dot product equals 0. Okay? Parallel if one is a scalar multiple of the other. Parallel also means that the cross product is a zero vector. It also means that the magnitude of the cross product is a zero scalar. So when we think orthogonal or perpendicular, the first thing that should come to mind means that the dot product is zero. So this means that if I take n and I dot product it with v, I don't know why I'm calling that v. Let's call this v. Then that would become zero. In other words, my ABC dot product with x minus x naught, comma, y minus y naught, comma, z minus z naught equals zero. This is the equation of a plane. This is the vector form of the equation of a plane. And it's not commonly used. What we do is just actually take the dot product. If we take the dot product, we would see A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals zero. This is the scalar equation of a plane. Because it doesn't involve any vectors. So that's what Jason typed in the chat box a little while ago. That's how we got to it, maybe. Okay, so that's the, if we take the dot product, this is the equation of a plane. So this is the equation of a plane that passes through the coordinates x naught, y naught, z naught, and ABC is the components of the normal vector. Notice that we can expand this to look like ax plus by plus cz equals some constant d. And still, we'd be able to recognize that a, b, c, the coefficients of x, y, z, are the components of the normal vector. So whenever you see an equation that looks like this, it is the equation of a plane. If you want to find out what the normal vector to that plane is, you simply take the coefficients of x, y, z. Now in this form, when it's expanded and grouped like this, you can't really identify the coordinates that it passes through right away. But in this form, it's much nicer. You can actually see a point that it passes through just by looking at the equation. Therefore, this is a more convenient point to look at. And when you find the equation of a plane, chances are this is what we're going to want. That leads us to these two equations that I put in boxes here. Let's move these guys up. Okay, so we know that this dot product is going to be zero. It's hard to see the dot there, so let me emphasize this a little bit. Which, when you take the dot product and write it out, this is the equation of a plane. So the scalar equation of a plane with normal vector ABC that passes through the point x naught, y naught, z naught is this equation here. And this is the one I want you to have memorized. So if someone asks you for the equation of a plane, That's it. You can also notice here that if I plug in A equals M, B equals 1, and C equals 0, I can rearrange to write this in the form y equals mx plus b, by the way. So y equals mx plus b is actually the equation of a plane. So there. All right. One thing that we do want to know how to do relatively quickly is sketching planes. So let's actually just get that out the way, sketching planes. Now we looked at some sort of planes last class or 2 classes ago, where we actually sketched the planes like y equals a constant, z equals a constant, x equals a constant. But what if the plane is not parallel to one of the axes? Then you can actually sketch the plane in some other way. One thing we like to do, and this is something that we're going to do more generally later on, is find the intercepts first. Then connect them with lines. And that's going to be how you this is going to be how you visualize a plane. So for example, if you want to find, you would find the x-intercept. This is when y equals z equals 0. If you plug that into the first equation, you would get x equals 3. You can then find the y-intercept. And you don't have to write this out. You can just like cover things up with your finger and do it in your mind. It's okay. You would get x equals 0 equals z, and so you get y equals 6. Z-intercept, plug in x equals y equals 0, you would get z equals 2. Now, this part, you can do this in your mind. You don't have to write this out. But ultimately now, what that leads us to is that I can now go to my axes and I can plot these points. So I can have x equals 3. So I go right here. That's 3. Y equals 6. And z equals 2. Then I would just connect those with a line. Boom. 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 And that is the plane, slicing through the first octant, like how you see there. Now it does go on forever in these directions, but the part of it, the phase of that plane that actually cuts through the first octant, it's going to slice through looking like a triangle like that. But of course it goes on forever. But this will be how we would sketch this plane. In most contexts, in this class or in other classes like it in the next class as well, you want to sketch a plane, that's how you're going to sketch it. Find all the intercept, connects the dots. And that object, that 2D object that you see there is the plane. Yeah, so that's the equation of a plane. You need to have that memorized. Take a picture of it right now because we're going to use it. Well, unfortunately, I can't have you draw a plane for the exam because it's online, unless, yeah, I could actually draw it and have you guys scan it and send it in. I'm gonna have that question just for Kayla. Like, if this is Kayla, you need to do this. All right. We're gonna do some examples. After some things to note here about planes. Two planes are parallel if their normal vectors are parallel. So if we want to measure two planes are parallel, it means their normal vectors would point in the same direction. So the parallel planes means I have a plane right here, and I have another plane below it. How do I know they're parallel? Well, I measure the normal vector of one of them and measure the normal vector of the second one. And if N1 is parallel to N2, the planes are parallel. Now we can talk about the angle between two planes. So let's say I have a plane here doing its thing. There's another plane slicing through that one. And if I was concerned with, say, the angle between these guys, let's say theta, then the angle that these planes meet at is also going to be the same angle that their normal vectors meet at. So here, if I go over here, N1, and then I pick a normal vector over here, N2, then it turns out the angle between N2 and N1 is going to be that same angle. So then I would be able to say theta is equal to the angle between these two vectors. And in fact, we know how to find that. It's the cross product. It's the inverse cosine of the dot products divided by the magnitudes, the product of the magnitudes. We learned that yesterday. Okay, so if you want to find the angle between two planes, it's the angle between their normal vectors. If you want to know if two planes are parallel, then it means that their normal vectors are parallel. Two planes are orthogonal if their normal vectors are orthogonal, etc. So all of that we can know. Now let's do some examples. And I wrote some of these in red because I actually expected to do this yesterday, and I expected to rush until we get to this point, and then I would just leave you guys with these to do. As you can see, I'm very ambitious sometimes. All right, so let's get through these. Find the equation of the plane that passes through this point with that normal vector. Now, this is the hardest one of the examples, of course, so I'm going to take this. I'll take one for you guys. You know, I got you. I'll take one for the team. So I'll do this one, you guys do the other two. All right. So here, I can just realize that take x naught, y naught, z naught equals 1, 2, 3. And n equals a, b, c to be that vector. Then the equation of the plane is just going to be -1 times x minus 1 plus 7 times y minus 2 plus 4 times z minus 3 equals 0. That's it, scalar equation. And you can stop there. And this is basically just me using a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So that's the equation of the plane. Yes, I took one for the team. Now it's Natalie's turn since she decided to say something. I know, this one goes out to Kayla because she decided to make fun of Natalie. Let's do both. We can not do this one. Kayla, do this one. Maybe try these. Maybe you guys take 3 minutes and do one of them. So at the end of the 3 minutes, I'll ask you guys what you did. Now, this is the answer that you should get. Right, so the first one, if I did expanded form for the equation of a plane, it should be 4x minus 3y plus 4z equals 10. And the answer to the second one is 8x plus y minus 2z equals 31. So try these guys. So either get to the answer or make sure at the very least, in like 2-ish minutes, you should have like a strategy for how to get to the answer. Remember, you're training grasshoppers. You know everything to figure this out. All right, squad, where are we at? Let's go with the first one. All right, give me a strategy. What do we do here? Maybe even tell me the answer. What do you think is the answer? strategy, ideas? How do we attack this? Anyone?
You know the formula is A parentheses x minus x0 plus B parentheses y minus y0
Yeah.
plus C parentheses z minus z0. You know that, right?
Yes, I know that. Yes. You know that.
So
It's good.
with
All
this
right.
three coordinate systems, you have to figure a way to make it look like, the vector, like the equation of the plane. You have to do
Okay. How do you do
that
it?
format.
So we know the goal. How do I get there? Jason, you've gone quiet.
Oh,
Normally you would subtract, from the higher coordinates,
Hold on. I think someone else was coming in. What?
Yeah, that's me now.
Yeah.
So since you gave us 3 points, I just plotted all three of them on the plane.
Okay, so drawing a picture, good idea. So let's
Yeah.
just draw a plane and actually put in those 3 points.
Yeah, so the first point on the left I put is 1, 2, 3. Then on the top I put 3, 2, 1. On the bottom I put -1, -2, and 2.
Mhm.
And I just took the final minus initial to create 2 vectors.
Okay.
So for the first vector, I got
Which 2 did you connect?
Oh, I connected the top one, 3, 2, 1,
Yeah.
minus the 1, 2, 3, and then the
So
-1,
you created a
-2.
vector going here.
Yeah.
And then you created another vector from the 1, 2, 3 again.
Yeah, from the 1, 2, 3 to the one on the bottom.
Okay.
And
All
then
right.
I did.
So
Yeah.
let's call this B and let's call this A. Tell me how you got to A.
Oh, so for A, I did -1, -1. I took the final minus initial.
Right.
So I
So
got
this one would be 2, 0, minus 2.
Yeah. And then for the other one, I got -2, -4, and -1. And then I took a cross product of both of them.
Why did you take a cross product?
To find the perpendicular, yeah.
We looked at this last time. So to create a vector that's normal to a plane, you can use it has to be normal to all vectors that are in the plane. So then for my n, I can just take a cross product. Now what I can do is sometimes I just drawing right over this so I don't waste space. I, j, k. And so now my normal vector is going to be, well, 0, -8, comma, -2, -4, which is -6, and then you get a positive, and then you would get -8, 0. So did you get that?
Yeah, that's what I got.
Okay, so now.
That's where I stopped. Correct. I ran out of time.
Okay, but that, from this point, that should be your ABC. And then for your x0, y0, z0, you can take any point. Take any point for x0, y0, z0. Name any of the 3 points that were mentioned. So say 1, 2, 3.
Yeah.
And so from that, I can actually do the equation of the plane. So the equation of the plane is A x minus 1 plus B y minus 2 plus C z minus 3 equals 0. And that would be the equation of your plane. So here's the thing now. Now here's the benefit of writing the answer in this version versus that version. Because this version here was actually the answer as it looked in the back of a textbook. I forgot even which textbook I took this from, right? So they would write the answer like this because depending on which point a student picks to put this in and depending on how they took a cross product and who they took, they'd get a scaled version of this. So their answers can look very different. However, if everyone multiplies out and writes it in one form, like this form, where everyone's an integer, then everyone would get the answer looking the same. So let's just make sure that this is the right answer. Let's verify the answer. Now, this will be good enough normally, but let's say you had this answer choice in a multiple choice quiz, how you would know that that's the answer. Let's verify the answer. First of all, notice that your normal vector can be scaled. So from the very beginning, I could have divided through by 2 here and wrote this as -4, 3, -4, but I can do that here as well. So this is equal to divide through by 2. Multiply out. Bring all the constants to one side. So this is going to be -4 plus 6 minus 12. That gives me -10. Now, if I multiply by -1, I would get 4x minus 3y plus 4z equals 10. And if you look here, that was the answer. So it's the same. But yeah, the trick here was to use the cross product. I know a lot of people was invoking this a lot earlier. Oh, cross product, dot product. You guys need to know how and when to use these guys that I'm teaching you about. And was that Natalie who was talking?
Yeah, that was me.
Okay, cool. So you got it.
Yeah.
Did it, boys. Right, Kayla, you ready? Are you there? His palms are sweaty. Knees weak, arms are heavy. Okay. Did you come up with an idea here?
I have an idea.
Okay.
I just don't know how to get from the idea to the answer.
Okay,
but
tell me the
like
idea.
We could start.
Tell me the idea.
So what I do is that I first wrote down the point. So 3, 5, -1.
Okay.
And then I broke up the line into dot product form. So I have line 1 is equal to vector 4, -1, 0 times t vector -1, 2, -3.
Plus t, plus, right?
Oh,
so
plus
this,
t.
yeah. Okay.
And then I set the point as and then I set the given point as x0, y0, z0.
So that's this one that you're saying is x0, y0, z0?
Yes.
Okay.
Yes.
And what did you do with that?
And so then from there, I decided to use the scalar equation of the plane.
Mm-hmm.
And that's where I kind of got stuck because I wasn't sure. Okay, so I know that x0, y0, z0, they go into the scalar equation, but I'm not sure if
How to find the normal. How would you get to the normal?
Yeah. Well,
so this is another situation where drawing would actually be very helpful. So let's say I put it in a picture. So you wrote down your points, but maybe a picture would have been nicer. There's my plane. Let's say this is my point, 3, 5, 1, -1. And there's a line that's in the plane. So this is a line in the plane over here. So that's the line, and it's parallel to the plane. It's in fact in the plane. It's intersecting the plane at all points on the line. We also know, based on what you just wrote, that the vector running along this line, I know what that vector is. That is the vector -1, 2, -3. Okay, with this picture, could you figure out how to get a normal vector?
Yes.
How?
Wouldn't you find, would you do a cross product? Like
With
the,
what?
wait. Would you find another vector
How?
from, oh no,
Can we find another vector? Because if we can, then we could do exactly the same strategy up here, right? If I have two vectors in the plane, we're
Yeah.
golden, right? So now the
Yeah.
question is, do we have enough to create another vector? How could we create another vector?
I feel like we do, but it's just flying right over my head.
In the equation of a line, we use the vector part, right? We use this part. What is this
Yes.
part?
But that's a point.
That's a point where? That's a point on the line, right?
Yes.
So
So
there's
then
literally a
just
point on the line
multiply.
right here. That's 4 comma minus 1 comma 0. Can you create a vector?
Yes.
How?
You start from, so to find a vector, you do final minus initial. So your initial point would be 4, -1, 0.
Yeah,
And your
create a
terminal would be
vector that
2,
goes
5.
from the point on the line that we know to hit this other point that we know. That's another vector. So
And so then
again,
you would have,
I can call that vector A. I can call this vector B. And so yeah, you do the final minus initial to get this other vector.
Yeah.
So your
and
A,
your other vector would be -1, 6, -1. Yeah. And then you can
Right.
do a cross product.
and then you can do a cross product with those guys. So -1, 2, -3. And then using those two vectors, we can get a third vector, which is by cross producting these. So I just throw these guys into a matrix, I, J, K. That is going to give me the N. So I block out the I column. So it's 6 times -3, which is -18, plus 2. Then it would be 3 minus 1. So it's -2. Then it would be -2 plus 6, 4. Did you guys get that? By the way, this is equivalent. I can scale it to not have such big numbers. Maybe divide through by a -2.
Yeah.
Then I can just use that as the ABC. And then set the other point, what was this? 3, 5, -1 as the X, not Y, not Z. And so this means the equation is A times X minus 3 plus B times Y minus 5 plus C times Z minus a -1 equals 0. So as you guys can see, the equations themselves aren't very difficult to understand. The difficulty comes in when someone describes a situation to you. They describe some sort of physical situation to you, and you need to be like MacGyver, and you need to like use what was given to figure out how to get the components that you need to get to the equations that were required. One thing that is definitely, I don't recall if I typed this out, so I'll just write it here. For a line, you should know what you need and then know how to get there. So for a line, you need a point and a parallel vector, which means however you can get the point and the parallel vector, that's what you need to do. For a plane, you need a point and a normal vector. Now, normal vectors, what's going on for a normal vector, we know about how to get a vector that's normal to two other vectors. So that's what the cross product is about. So when it comes to planes, a normal vector is going to be a very common thing to show up. Dot products won't normally show up in these scenarios because a dot product gives you a scalar. So when we need vectors, a dot product is never going to be, yeah, good. That's why I didn't just do the problems. I wanted you guys to actually try it because I know you guys can figure it out. So whenever you're looking for the equation of a line, it's very important for you to find a point and a parallel vector. When you're looking for the equation of a plane, it's very important that you find a point and a normal vector. So by using what we have to figure out what these guys are, we can figure out the equations of lines. That was that. What I'm going to do now is I'm just going to explain two concepts to you, and then we're going to end. Going to be very quick. I'm not going to do the examples. So we'll start tomorrow's class with just doing the examples. But for now, I'm going to explain two other things. And it'll take me like 5 minutes, and then we'll get up. So we want to find some distances. And it turns out that, was there a second part to this? Or was I just going down aimlessly? Another thing that we need to know is about how to find the distance between a point and a line or a point and a plane. So here's how we would do that. So point and a line. Let's say I have a line here. There's a point out here. Call that P. I care about finding the distance here, D. So I know the line and I know the point. I want to know how far the point is from the line. Turns out that we can figure this out using vectors. So I can find a point on the line, use a vector to connect that point to the P. Let's call that B. Suppose the direction vector along the line is A. Then if I know the angle here, theta, then it turns out that my D is just going to be the magnitude of B sine theta. Of course, that would mean that my D is the magnitude of B sine theta. And I can do this little thing where I multiply and divide by the magnitude of A. You will realize that this thing is something that we know. That, for those of you paying attention, is the magnitude of the cross product. So it turns out that's a form that we can use to find the distance between a point and a line. So a distance between a point and a line where the point is P and the line has direction vector A, it's going to be A cross B, the magnitude of that, divided by the magnitude of A. And B is just a vector from the line to the point. So that's a form that you can use to find the distance between a point and a line. What about the distance between a point and a plane? Well, let's say here's my plane. Here's my point over here, not on the plane. Again, I can find a point in the plane, some specific point, and I can connect that to P. Notice here also that I can have a normal vector to the plane that goes up and hits P. So that's my normal vector N. The vector from the point to the plane is B. Now we're going to use some that I spoke about yesterday. What we're going to do is we're going to project the shadow of B onto the vector N and then calculate the length of that shadow. In other words, we can use a scalar projection. So if the length here is D, notice that D would be the magnitude of the component of B onto N. Project the shadow of B onto N and measure the length of that shadow. We also have a formula for that. That would just be B dot product with N divided by the magnitude of n, based on what we said yesterday. So that leads us to this other formula that I was trying to scroll down to reach. That leads us to this. And that's the distance from a point to a plane. So I will leave up these two examples for you guys to try. Try it on your own. I'll ask you guys about it tomorrow in the beginning of class. We'll start with these examples and then move on. But for now, that is, that's the end. So I'll leave these guys in the PDF for you guys to try. So, and that's it. So hopefully that was a fun lecture, very informative. Now we know that we've been lied to our entire lives. This wasn't the equation of a line. We now know what the equation of a line actually looks like and what the equation of a plane is. And hopefully you can go through all sorts of different scenarios. It will be in your homework. We have to figure out, given this information, how do I use that to figure out this guy? And you just need to know, when I want to find a line, I need to find these two things. If I want to find a plane, I need to find these two things. And then you need to know how to use cross products, dot products. Well, dot products aren't going to come very often. Cross products are creating vectors, connecting different points. You need to know how to use all the things that I was telling you about vectors to help you figure out these equations. Anyway, hopefully you had fun, and good job for those of you figuring out. Good job, Kayla, Jason, and Natalie, for a lot of your input. And we had a lot of people who, they didn't really say anything, but they were giving very helpful hints in the comments. I think Abdullah and Abdul Rahman and some other people. Memphis was also going in there. So nice, good coming together, good effort, team. We'll end there. That's it, and I will, good night, stay safe, and I'll see you in the next one. Ciao.